Okay, well, thank you to the organizers for having me here. I'm really excited to talk to you all about extreme adaptive optics for the next generation of ground-based telescopes, and also talk a little bit about the synergies between adaptive optics for both ground and space-based telescopes. Okay, there's my title slide. I'm here at UC Santa Cruz since the retirement of Claire Max. I'm also the director of the Center for Adaptive Optics, and so I'm very pleased to show any of you here our labs while you're here as well. Okay, so I wanted to start my talk with one of the most famous direct images of a planetary system, and that's Voyager 1's image of 6 planets in our own solar system, including Carl Sagan's famous pale blue dot image of the Earth. Now, Carl Sagan said the Earth was suspended in a sunbeam. That's the kind of instrument-based optical aberration that people who work in adaptive optics would like to mitigate. Okay, now, since 1990, exoplanet scientists have placed the planets in our solar system in the broader context of planet formation in our local solar neighborhood, and then through microlensing also in our galaxy. And so you can see a couple of things from this figure. First of all, you can see that the planets in our solar system oftentimes occupy an area of parameter space when it comes to planet mass and separation that is not well probed by the exoplanets that have been discovered by all of these diverse methods of detection. But what I want to spend the most time talking about in this talk today are those planets you see in orange in the upper right-hand corner of this figure. These are the planets that we have directly imaged. So we have formed an image of the planet that is spatially separated from the image of the star. And why are these important? Well, it allows us to, as the previous speaker discussed, disperse their light into a spectrum. We can then use that spectrum to understand the physics and chemistry of these planets' atmospheres and one day look for life. So why are all of these directly imaged planets in this high separation, high mass regime? Part of that has to do with the technological difficulties of directly imaging a planet. So that's what I'm going to describe to you now. Okay, so if we imagine a star emitting light in all directions, that light is an electromagnetic field which has an amplitude and a phase. And it has these surfaces of constant phase as the light propagates outward. For a star, those would be spherical shells of constant phase in 2D circles. Now, by the time these surfaces of constant phase, which we call wave fronts, have made it to us, the observer, they're so stretched out that we can imagine them as being pretty much flat. Okay, so now, if we have an idealized spacecraft, we can form an image of the star. Of course, we'd see this airy pattern with a core that has the size, the wavelength lambda over diameter of the telescope d. So if you want to directly image a planet, your next task is going to be to try to suppress the light of those airy rings so that you can see extremely faint planets very close in to that star. And the way that that's been done so far by astronomers is using devices called coronagraphs. Now, there is a huge diversity of types of coronagraphs, but many of them work in the following way. We put one mask at the focal plane, so we bring the light to a focus, and then we block out that innermost lambda over d part of the light. And then we bring the light rays parallel again. And then we put what we call a LEO mask, which is oftentimes sort of a washer or a ring-shaped mask when the light rays are parallel. When we bring the light back to a focus, we've then at least partially suppressed those airy rings from the star, and we can directly image exoplanets. So the example that I'm showing here is a multi-planet directly imaged system, HR 8799, where in this image you can see 3 of the 4 planets that have been directly imaged around that star. Okay, now what if we don't have an idealized space telescope? What if there are aberrations that are imparted through, say, scratches and imperfections on the lenses and the mirrors of that telescope? Or perhaps we have pointing jitter, or perhaps that we have some thermal evolution over time. In that situation, we need to actively flatten that wavefront. And this is where adaptive optics, or a more specific way of referring to this is wavefront sensing, comes in. So these surfaces of constant phase, these wavefronts, have now been aberrative. They've been twisted and pulled by the imperfections in the optics in these instruments. We then bounce these off of what we call a deformable mirror. So you can imagine a funhouse mirror whose surface you can pull and push to then counteract those aberrations. But how do we know what shape to give that deformable mirror? Well, we can break off some of the light and send it to what we call a wavefront sensor. And so there are many types of wavefront sensors, but a particularly intuitive one is called the Shack-Hartman wavefront sensor. So imagine you put a grid of tiny lenses in front of your light. Well, then you would see this grid of spots behind the lenses. If the wavefronts are not flat, that changes the centroids of those spots. So that's one way that you can find out what is the local slope of the wavefront in a spatial way. So then we compute, based on our wavefront sensor, what shape we should have for that deformable mirror. Hopefully, we flatten the wavefront so that the coronagraph can then do its job of suppressing the starlight. Okay, now this situation is very similar between the space and the ground in that we have aberrated wavefronts and we're trying to flatten them. On the ground, it's just that your job is made a lot harder by the presence of the atmosphere. So as these starlights, pristine flat wavefronts, propagate through the Earth's atmosphere, they go through different pockets of air in the atmosphere that have different temperatures and therefore different indices of refraction. So the Earth's atmosphere itself is going to aberrate that wavefront in addition to the optics of your own telescope and instrument. So now, if you form an image of a star with a ground-based telescope, instead of having this perfect lambda over d sized point spread function, you have this tremendous mess whose size is determined by the size scale of atmospheric turbulence, not by the size of your telescope for large telescopes. Okay, so on the ground, we have to run our adaptive optics systems much faster to keep up with atmospheric turbulence. So we're talking kilohertz speeds, 1 kilohertz even up to 3 or more kilohertz speeds. And we also have to correct for higher amplitude turbulence introduced by the atmosphere. Okay, now why are we bothering to do exoplanet imaging from the ground when you can see it would be a whole lot easier from space? Well, it has to do with the size of the telescopes involved. So Habitable Worlds Observatory, which is about 6 meters, is what the decadal survey said, which is the same size of JWST. As you can see, that size is dwarfed by the coming extremely large telescopes that we'll have here on the ground. The Giant Magellan Telescope up to the 40-meter European Extremely Large Telescope. So these different telescope sizes allow us to access complementary regions of parameter space when it comes to the mass of the planet that we want to observe and how close that planet is to its star. And the previous speaker touched on the same concept. But here we're showing that for the next generation of space-based telescopes, those are going to be able to observe low-mass planets on this figure, wider separations from their host stars. So hopefully those will be able to access the habitable zones of solar-type stars. Whereas the next generation of ground-based telescopes is going to be able to get in much closer to the star because their diameter is so much larger, but it won't be able to dig down as deep as those space-based telescopes. Now, fortunately for us, that allows the ground-based telescopes to do something that's very complementary to space, and that is ground-based telescopes can access the rocky planets in the habitable zones of the nearest M-type stars, whereas the space-based telescopes will access the habitable zones of the nearest solar-type stars. We need both of these to form a complete picture of habitable zone exoplanets in our local neighborhood. Each of them is indispensable. Okay, so why have I shown these two very separate lines to indicate the performance of these next-generation ground-based telescopes? So the upper line indicates the kind of performance we would get in terms of how faint of a planet compared to the star could you detect versus separation. If we were to take modern high-contrast imaging systems, like, say, the Gemini Planet Imager, and just stick them on a larger telescope, that's about the performance you would get. The lower curve, or line, is the kind of performance that we think we could achieve if we overcame some of the major technological barriers for adaptive optics and high-contrast exoplanet imaging today. So for the rest of this talk, I'm going to tell you about what, in my view, are some of those most exciting areas. So now I want to touch on a fundamental limit to the performance of an adaptive optics system, and that's its time delay. So you can imagine you always have to have some exposure time on a wavefront sensing detector to collect photons from your star so that you can correctly measure the shape of the wavefront and know what shape to give the deformable mirror. So no matter what technology you use, that time delay between sensing and control is never going to be zero. So I got pretty excited a couple of years ago when our colleagues Olivier Guillon and Jared Males, introduced a method of predicting the wavefront, so predictive wavefront control, that's just based on your previous wavefront measurements. So what we do is we create this very simple linear least squares, linear algebra problem, where we say, I want to create some predictive filter that I can apply to my last couple measurements of the wavefront, and I'm going to train it using a large set of training data, and that's how I'm going to compute my filter, and then I'll apply that in real time to try to compensate for that time delay. And so we were excited about the potential impact of this method because when we use state-of-the-art high contrast imaging systems like Gemini Planet Imager and like Sphere over on the VLT, we commonly see this feature in our raw data. This is an example of raw coronagraphic data that you see here, where we have this sort of butterfly shape. This is called the wind butterfly or the wind-driven halo. And this is an artifact in our image. We would like this whole image to be dark, but we have this feature because the wind is blowing preferentially in one direction. And so our adaptive optics system is having a hard time keeping up with the evolution of atmospheric turbulence in a way that corresponds with that direction. So if you had a low-mass exoplanet located right on this wind butterfly, which is taking up half our image, you'd be out of luck. Okay, oops. Oh, well, this is a real shame. Only one of my two curves is showing up on this slide. I'm not sure why. Okay, so after we understood that we wanted to implement this new method of predictive wavefront control, my philosophy was I want to get this on sky as soon as possible because even though the simulations were very exciting, simulations were showing that if you do this predictive wavefront control, perhaps you would achieve orders of magnitude contrast improvement. I wanted to know if I deployed this at my local observatory, WM Keck Observatory, what might that benefit be in reality, and then how could I tackle those real world problems that might be limiting our performance? So I got together with a postdoc in my group who's now an AO scientist at NRC, Micah Van Coten, and we worked with the Keck Adaptive Optics team to implement this method on the Keck AO system. And okay, only one of the curves is showing up on this figure. Fortunately, it's my favorite curve. It's the predictive control one. But what we found is that our contrast, so how faint of a planet compared to its star we could observe, was about 2 to 3 times better when we implemented the predictive control compared with the standard controller. So that was a really exciting performance upgrade to us, but of course it's not the same as that several orders of magnitude improvement that we might have thought based on a simulation alone. So now our tough task is to say how can we bring our on-sky performance closer to what we might expect from predictions. There are a bunch of issues in that vein that we can address. Some of them are more tractable than others. So for a more tractable issue, there are a lot of different tuning filters that you can play with as you're creating your predictive filter. So that's one thing we've been doing recently is understanding how to optimize that filter's performance. There's also trying to better calibrate your adaptive optics system. So perhaps your measurement of the wavefront has some systematic biases in what you measured it to be. And then there's the more pessimistic issues, which is perhaps the atmosphere is simply not as predictable as our simulations would have us believe. And so that's what I'm interested in working on in the near future, is how much of an improvement can we realize with this fundamental issue of overcoming the time delay in an AO system. You might think at this point, this sounds like a really ground-specific issue. This is also useful for space because there are some high time cadence issues for a space-based high contrast imaging system. For example, the pointing jitter and reaction wheel jitter that this can be used for as well. Okay, now the second topic I want to discuss, again, has to do with something that ground and space have in common. And that is that all of these future observatories have segmented primary mirrors. That's true of JWST. That's going to be true of all of these future ground-based extremely large telescopes. It's also true, conveniently, of Keck Observatory. And this is an issue, potentially, for high contrast imaging, because if you have incorrectly moved the segments relative to one another, so let's say you'd like to have your segments perfectly aligned, but in actuality, they have some offset to them, that will hurt the performance of your coronagraph. So for something like Habitable Worlds Observatory, you need picometer level control of those mirror segments. That's extremely challenging. On the ground, it's not quite as grim. We're dealing with nanometers and tenths of nanometers precision. But this is not a solved problem on the ground. So at Keck Observatory, which is in this picture, you see it's a segmented primary mirror. It comes up for us from time to time that we have this kind of staircase mode going across the mirror where the segments are all kind of shifted relative to one another as you move across the primary mirror. And the result of that is that when we turn on our adaptive optics system, we try to make a perfect point spread function. Instead, what we see are these artifacts that we call speckles. They look a lot like planets, don't they? That's always really frustrating for us when we see artifacts like this. So this is the kind of artifact that by controlling the primary mirror in closed loop during a science observation that we can mitigate these problems. Now, the challenge is that most of our favorite types of wavefront sensors, like the Shack-Hartman I showed you a picture of, aren't very good at detecting these phase discontinuities that you get when you have a misaligned primary mirror. So we needed to use a different kind of wavefront sensor. So what we're using at Keck is a wavefront sensor that was actually invented for microscopy in the 1950s. It's called the Zernike wavefront sensor. And it's really elegantly simple. It just is an optic that you put when you bring the light to a focus, and you just introduce a little phase shift or a phase dimple to that innermost lambda over d of your starlight. And it turns out that then when you make those light rays parallel again and you form an image, what you've done is you've interfered some of that starlight with itself. And so the intensity of that final image has some relationship with the phase that you're trying to measure, and in such a way that it's pretty insensitive to these phase discontinuities. So this sensor hadn't been ever used on a segmented telescope before, so we were really excited in the last couple of years when we had a chance to work with our collaborators on the Keck Planet Imager and Characterizer, KPIC. This is the Caltech and JPL team, to actually install this Zernike wavefront sensor inside the Keck adaptive optics system. So we installed it in there, and then we intentionally kicked 3 of our primary mirror segments. So that's what this image is indicating here, or which segments we kicked. And then the other image that you see is one of our almost raw images from the Zernike wavefront sensor, where sure enough, the intensity that we saw was indicative of which segments that we had kicked. And so we've been working on characterizing the performance of the Zernike wavefront sensor. So we are intentionally moving segments in smaller and smaller amounts to try to help us understand the limitations of the Zernike's performance. Coincidentally, the Zernike is also being used on the coronagraphic instrument of the Roman telescope, but in a very different context. So Roman is a monolithic mirror, it's not segmented, but just because the Zernike is a really high-quality wavefront sensor for low-order aberrations, they're using it just for that particular purpose. Okay, so in the interest of time, I also want to say we have a even more exciting version of the Zernike wavefront sensor that allows you to detect even larger offsets to your mirror. That's what we have on Sky now, and that's what, together with my postdoc Maisa Salama, the sensor whose performance we're now characterizing. So what really excites me about this Zernike wavefront sensor work is that even though we have very different regimes of primary mirror stability that we have to deal with on the ground in space, we're dealing with all the same problems as the space-based telescopes. We're dealing with how well can we phase up the mirror using sort of a set and forget method, which is what we do at Keck currently, and then what's the benefit of dynamically controlling the mirror using something like a Zernike during a science observation. Okay, the last thing I want to mention is that we have a real challenge, as you can probably imagine, getting a lot of that good on-sky time that allows us to develop these new adaptive optic techniques on Sky. And so a really important avenue for the future will be building test beds that we can have access to here at universities that have common software with our AO systems at the observatory. This will allow us to develop new techniques together with our junior scientists on university campuses and then deploy them as seamlessly as possible on Sky. And so that's what we're trying to do here with our new test bed, the Santa Cruz Extreme AO Lab. So this runs the same software as we run at Keck. And we've already made a lot of fun progress developing software for the Zernike wavefront sensor and then deploying it pretty much as is at the observatory. So with that, I'm just going to thank our teams at UCSC and Keck, and I look forward to talking to you all in the Q&A session.